Hello all. So in this session, I would like to talk about multimodal networks and image captioning. So when I talk about image captioning, we will look into MCOCO dataset. A picture is worth 1,000 words is a famous quote that we often hear, right? So in this session, we'll put this quote to the test and generate captions for an image. In doing so, will work with multimodal networks. Okay, so far we have operated on text as inputs. Humans can handle multiple sensory inputs together to make sense of the environment around them. So recent advancements in image, speech, and text processing lay a solid foundation for multimodal networks. In this session, transitions from the world of NLP to the world of multimodal learning, where we will combine visual and textual features and then look into some few of the concepts. Okay, so when I talk about this multimodal deep learning, the dictionary definition of modality states that it is a particular mode in which something exists or is experienced or expressed. So sensor when I talk about sensory modalities, like, when I talk about the human modalities, we take into consideration touch, taste, smell, vision, sound, which basically allows the humans to experience the world around them. Suppose you are out of the farm picking out to the farm picking strawberries, okay, and all of a sudden your friend tells you to pick up ripe and red strawberries. Okay, so the instruction ripe and red strawberries is processed, and this would be converted into a visual and haptic criterion. Okay, so as you see the strawberries and feel them, you'll understand that you should map the criteria, that is red and ripe strawberries. Okay, so this task is an example of multiple modalities working together for a task. Okay, so as you can imagine, these capabilities are essential for robotics. Okay, so as a direct application of these examples, there was a research paper titled Hearing Lips and Seeing Voices. Okay, so that was in a reputed journal. This paper was published, where we understand about few of the visualization concepts. Okay, now speech recognition models, basically when we talk about, they use lip reading information, which were developed in the field of audio visual speech recognition, which are in general called as AVSRs. There are several exciting applications of multimodal deep learning models in medical devices, medical diagnosis, learning technology, and other artificial intelligence areas. So, in order to deeply understand this, let us drill down into specific iteration or specific interaction of vision and language and the various tasks that we can perform. Okay, so the first one which I would like to discuss is vision and language tasks. Okay, so in the last semester we have studied about computer vision, right? Deep learning with computer vision. So a combination of computer vision and natural language processing will actually allow us to build smart AI systems that can see and talk. Computer vision is all about, seeing. Natural language processing is all about talking. So we can build so many systems that can actually see and talk with respect to CV and NLP. Okay, so CV and NLP together will actually produce very interesting task for model development. Taking an image, generating a caption for it is a well-known task for all of us, right? So a practical application of this task is generating, text tags for images on web pages. Like all of us use Facebook, right? So automatic, image recognition and the caption given to the picture is all about different real-time applications that we use in our day-to-day lives. So visually impaired readers use screen readers, which can read these tags while reading the page, improving the accessibility of web pages for them. Okay, so other topics in this area include video captioning, storytelling, okay, composing a story from sequence of images, etc. So when you look into this, the following images shows how some examples of images and captions are generated. Our primary focus in this chapter is on image captioning. Okay, so as you can look into the figure, there are 4 images and each caption is generated for the images. Okay, now the next topic that I would like to talk about is visual question answering. Now this is a challenging task of question answering about objects in the image. So the following images show some examples from VQA dataset, visual question answering dataset. Okay, so compared to image captioning that we have discussed before, where prominent objects are reflected in the caption, VQA is a more complex task. Okay, so answering the question may also require some reasoning. Okay, as you can see, consider the bottom right panel. Okay, in the following image, answering the question, does this person have 20 by 20 vision? If I ask, does this person have 20 by 20 vision, this requires reasoning. Okay, so data sets for VQ are available at visualqa.org. You can log into that and understand about this particular thing. Okay, so basically reasoning leads to another challenging but fascinating task, which is called as visual common sense reasoning. Okay, so when we look at an image, we can guess emotions, actions, and frame a hypothesis of what is happening. So such a task is quite easy for people, and may even happen without conscious effort. Okay, so basically the main aim of visual common sense reasoning is to build models that can perform such a task. Okay, so we are incorporating common sense before we actually answer to the questions for the images generated. Okay, so these models should also be able to explain or choose appropriate reason for the logic inference that we made. Okay, so as you can see here in the figure, we are trying to identify person wise emotions, or person wise what exactly are they doing, how are they sitting, their body language, whether they are cracking a joke, whether they're serious, and all the emotions can be visualized with common sense. Okay, so thus far we have gone from images to text. The reverse is also possible, and it is an active area of research. Okay, so in this task, images or videos are generated from text using GANs and other alternative architectures. Imagine being able to generate an illustrative comic book from the text of a story. This particular task is at the forefront of research currently, as all of us know about it, right? So another critical concept that comes into this area is visual grounding. Okay, so basically grounding enables us trying concepts in language to the real world. Simply put, it matches words to objects in a picture. So by combining computer vision, NLP, understanding the language, we can ground all these concepts from language to parts of an image. For example, if you want to talk about a short elephant and a short person, they have different measurements. Okay, so grounding basically provides us with a way to see what models are learning and helps us guide them in the right direction. Okay, so now that we have proper perspective on vision and language tasks, let's dive more deep into image captioning. Okay, now image captioning is all about describing the contents of an image. Basically, captions can help in content based image retrieval and visual search. Okay, so we already discussed how captions could improve the accessibility of websites by making it easier for screen readers to summarize the content of an image, right? So a caption can be considered basically as a summary of the image. Okay, so once we frame the problem as an image summarization problem, we can adapt to the sequence to sequence model that we've already learned in the previous chapter, etc. Okay, so in text summarization, the input is a sequence, which is a long form, and the output would be a short sequence summarizing the content. When we talk about image captioning, okay, the output is similar to format of summarization. However, it may not be obvious how the structure of an image that consists of pixels, or how do we read that image to make image captioning as output. Okay, so a naive solution for representing images, because basically when I talk about image captioning, the input is an image and output is a summarization of the text based upon the contents in the image. So basically a perfect solution for representing image as a sequence pixels. Suppose if you have image of 2 by 2, okay, so this total number of sequence would be 4 tokens. So if you take 28 by 28 pixels, the sequence of tokens would be 784. Okay, so when the tokens represent text, the embedding layer learns the representation of each token, and if this embedding layer has a dimension of 64, then each token would be represented by a 64 dimensional vector, and this dimensional vector that we are generating will be learned during training. Okay, and then after training, these 3 dimensions uh, you know does not sound like a logical approach, because most importantly pixel are laid out in 2D representations while the text is laid out in 1D representation. Okay, so this concept basically is represented here in the figure below. Okay, so the words are related to words next to each other when the pixels are laid out in sequence. Words are next, as you can see. Okay, whereas the pixels are laid in sequence. Okay, so here comes the concept of data locality. Okay, so data locality of these pixels is broken since the content of pixel is related to all the pixels around it. Okay, so not just the left and right of it. The idea is shown by following super zoomed in an image, as you can see here in the figure. Okay, so I majorly want to concentrate on data locality here. Data locality and translation invariance are two difficult properties, or two important critical properties of image. Okay, so translation invariance is the idea that an object can appear in various spots in an image. Okay, so multiple locations the object may appear. When we talk about a fully connected model, okay, the model would try to learn the position of the object, which would prevent the model from generalizing. Okay, when I talk about CNNs, okay, convolutional neural networks, these can be used to exploit these properties and extract signals from the image. Okay, when you're going for CNN at high level, we can use CNN, specifically the ResNet 50 architecture, to convert the image into tensor that can be fed to the sequence to sequence architecture, and then our model will combine the best of CNNs and RNNs to handle the image and text parts of the image under sequence to sequence model. Okay, so the following diagram that you can see here in the slide would actually show our architecture at a very high level. So CNN based, when you look into the image as input, CNN based feature extraction. From that, we'll go for visual encoder, and then we'll decode, and then the images will be generated with a caption. Okay, so there are so many different steps that we adopt for building our model. So basically these are the steps that I want to discuss about. First is we download the data given the large size of the data set, because when we are dealing with images, obviously the size of the data set would be large. Okay, so we pre-process the captions. Okay, so captions are in JSON format. They're flattened into CSV for easier processing. This is one step of pre-processing. And then we extract the features from the image file using ResNet architecture. And then we use the transformers for training a fully modeled pre-trained transformer model with positional encoding, multi-head attention, encoder, decoder. Already we have discussed in the last chapter. We use all this. And then using the trained model, we apply to inference and try to generate some captions. And after we generate captions, we also try to evaluate the performance using evaluation metrics like, blue bilingual evaluation under study scores, etc., to compare the trained models with the ground data. Okay, so if you want to work on image captioning, okay, I would prefer you to work with MS-COCO dataset. So Microsoft published this MS-COCO dataset, which is COCO represents common objects in context. Okay, in 2014, all the versions of this dataset can be found in cocodataset.org. Okay, so basically this COCO dataset is big dataset that's used for object detection, segmentation, image captioning, and other different applications related to image captioning. Okay, so you can focus on training and validation images. Okay, where 5 captions per images are available. Based on how the training is done, you can give your test data and check. Okay, so giving some features of we have different versions. Okay, I'm explaining about one version of COCO dataset. There are approximately 330,000 images, which cover 91 object types that are commonly found in day-to-day lives. Okay, so that is the reason we consider this as a standard dataset for image captioning applications. So each image has annotations that describe the objects within it. Okay, so when I talk about annotations, object detection can be done, segmentation can be done, captions can be generated, key point location also can be identified, etc. Okay, so we have training data set, validation data set, and test data set. The entire data set is divided into training data, test data, and validation data. So you can download the data set from MS-COCO official site. You can download images, you can download annotations, you can download combined packages. You can apply, once you work on image captioning application in the background, you can also use APIs and tools. MS-COCO provides an API for Python that can be used to access and manipulate the dataset. Okay, so this is all about what is multimodal deep learning, what is image captioning, and MS COCO data set that we actually use for working on with image captioning models. Thank you so much.